Welcome to the first lecture in Unit 8. This is titled One for You, Two for Me. And the quote we have is from Bug Bunny. It says, one for you, one for me, two for you, one, two for me, three for you, one, two, three for me. And this is our introduction to stoichiometry. And really, when we talk about stoichiometry, it is all about ratios. And so our learning goals for this. The main learning goals for this is students will be able to understand the role of that mole ratio, and that's the big thing in stoichiometric calculations. And in using this mole ratio, students will be able to convert between moles of a reactant or product to another reactant or product. And then lastly, students will be able to integrate their previous knowledge of dimensional analysis to include stoichiometry for any reactant or product. Big thing on that one, it's all about the math. And so this is a math heavy unit, but hopefully we're going to step through it and really talk about the mole ratio and talk about converting and use our dimensional analysis to really help us look at chemical reactions. So what we already know coming into this, that dimensional analysis is a useful tool for converting between two equivalent values. When we're looking at this, we use our statements of equality, we use our conversion factors, setting up in everything. So if we, in this example, we're looking at converting between 26.2 miles, which that's a marathon, into how many meters that is. And so when we look at both numbers in the vertical column, so both numbers here, those are equal. And so this is where we get our statements of equality, where we say that 1 kilometer is equal to 1,000 meters, and we see that one right here. And we see that 1.6 kilometers equals 1 mile, and we see that one here. Those are our statements of equality that we can use to convert. And so in this case, we converted from 26.2 miles to meters, which is 41,920 meters. What else do we know? We also know that the law of conservation of mass states that you must have an equal number of each atoms before and after reaction, but they can be arranged differently. So the law of conservation of mass means that we have to, whatever we start with is what we finish with. We start with the same number of molecules, we end with the same number of molecules, or the same number of atoms. And so that's the law of conservation of mass. What does this really mean? Balanced equations. And so when we talk about balanced equations, we're talking about the law of conservation of mass. Now what we kind of should have taken from the lab, what we should have learned from the lab, is that titration is a useful tool for qualitative or quantitative and qualitative analysis. So we can look at titration. Careful measurements of products and reactants allow to determine the determination of the ratio of products and reactants, and that the ratio can be useful in identifying and predicting reactions. And so we learned in the lab and looking at the different types of iron and copper through that titration, we can use that to figure things out about the reactants and the products. So, looking at what do chemical equations give us? When we're looking at this, we know that it gives us all the information, the qualitative information about is it a gas, is it a liquid, is it solid, is it aqueous, is there heat added to it? It gives us that information. But the chemical equation, what it really does is it shows us the mole ratio, and this comes from the coefficients. Now we see that we have a 1 2 1 2 ratio. What this really means is that we have, for every 1 mole of methane, 2 moles of oxygen. It produces 1 mole of carbon dioxide and 2 moles of water. Where do those coefficients come from? Well, we know that those coefficients come from that balanced chemical equation. And really, when we're talking about mole ratio, when we're talking about chemical equations, we're always talking about a balanced chemical equation. So using the mole ratio. How do we use the mole ratio? Well, the mole ratio, looking at those coefficients in front of them, the mole ratio allows you to predict the amount of each product. Okay, how many moles, in this example, how many moles of water will be produced when 25 moles of methane is combusted? Okay, so I'm trying to figure out, well, how much water am I going to get if I start with 25 moles of methane? Well, the mole ratio between methane and water is 1 to 2. So 1 mole of CH4 equals 2 moles of H2O. And this gives us a ratio. It gives us a statement of equality that we can use in dimensional analysis. And we set it up where the units cancel. The moles will cancel of methane. We're left with the moles of water. And then we just multiply the top. 25 times 2 will give us 50. And that's what the mole ratio allows us to do. It gives us a ratio between reactants and products to help us predict how much of each thing we're going to have. So, possible mole ratios for this reaction only. Just for this reaction, when we're looking at it, 1 mole of methane produces or needs 2 moles of O2. 2 moles of CO2 is 2 moles of H2O. 1 mole of CH4 is 1 mole of CO2. Now these ratios work for this reaction only. We'd have to have another reaction. We'd have to balance it if we have different things. But what we can say is that 1, 2, 1, 2, they equal each other. So we can say we can compare methane to oxygen, or we can compare methane to carbon dioxide, or we can compare methane to water, or we could compare oxygen to carbon dioxide, or we can compare oxygen to water. We can compare them all to each other because they're all set in a ratio to each other of 1 mole to 2 moles to 1 mole to 2 moles. So other common examples of ratios that we see, a basketball game is 1 basketball per 10 people. We know that there's 100 pennies per dollar, and in one day you have 1 day per 24 hours. Those are examples of ratios. That's what the mole ratio is. It's just a ratio comparing two things. But we can use it in dimensional analysis to help us determine amounts of products and reactants. So it says write the correct mole ratio for the moles of TNT to moles of nitrogen gas. Now TNT is this right here. Nitrogen gas is right there. We should know nitrogen gas. We probably might not know TNT. But when we're looking at this, what we see is that we have, look at their coefficients, a 4 to 6 ratio. So what we have is we have a 4 to 6 ratio. So for every 4 moles of TNT equals 6 moles of nitrogen gas. And that would be our mole ratio, is a 4 to 6 ratio. So looking at our next example, it says we have 35 moles of potassium permanganate are present in the sample that is mixed with hydrochloric acid according to the equation below. And so we're looking at the equation below, and what we can see is it's already balanced. We see our coefficients are in front, and it's nice and it's balanced. And the question that we have is how many moles of water would you expect? And so when we're looking at this, we want to go from our potassium permanganate to our water. And if we use our mole ratio, what we can say is we can say that 3 moles of our KMNO4, that those guys, not 3, but 2 of those guys, because that's a coefficient in front, it's 2. So 2 of those guys equals 8 waters, because that's a coefficient in front. So 8 moles of good old H2O. And so what we can do is we can set up this problem. When you're setting up any stoichiometry problem, you start with the number that it gives you in the problem. So we have 35 moles of our KMNO4. We set it up. And what we're looking at is, since we have moles of KMNO4 right there, we can take this part of the conversion factor, put it on bottom, and then take the other part of the conversion factor, put it on top, and we go ahead and multiply everything out. And so we multiply our 35 times our 8, all divided by 2, we should get 140 moles of water. Now, looking at stoichiometry again, just looking at the mole flow chart that we have now, what we've been doing is we've been just looking at mole to mole conversions and just using that mole ratio. But what we can do is we can go from grams to moles using gram formula mass, and then moles to mole conversions like what we've been doing to get any substance. And so when we're looking at it, we're looking at this problem right here. If we have 5,000 grams of our nitroglycerin and we want to move into moles of CO2, and so we're trying to figure out this, what we can do is anytime if we start at grams, we can go from grams to moles using the gram formula mass, and then we can use the mole ratio to figure out the moles of something else. In this case, this would be A and CO2 would be B. And so you can see that we did that. We went ahead and used our molar mass and then used our mole ratio. Now the one thing that you can write down here, anytime you see grams in a problem, you have to write down the molar mass. Anytime you see grams. So if I have 5,000 grams of nitroglycerin, I have to write down the conversion factor of molar mass, so that, or gram formula mass, that's the same thing. I have to write that down because I'm going to use it. So let's look at an example. So in an example here, what we see is that we have 50 grams of iron. So it said grams of iron, so guess what we have to write down about iron? We have to write down the molar mass of iron. And then it says reacts with excess oxygen to form iron 3 oxide. How many moles of iron 3 oxide are produced? And so when we're looking at this, what we can say is that we're looking first at iron, and then we're looking at iron 3 oxide. So the first thing we always write down in every single stoichiometry problem is we write down the mole ratio. So our mole ratio is 4 to 2. So we're going to go ahead and write that down. 4 moles of iron equals 2 moles of iron 3 oxide. Okay, that's the first thing that we always write down, and that's what we have here. Now, since it said grams, that G, by iron, we need the molar mass of iron. And so we can look on the periodic table, and molar mass means that 1 mole of any substance equals the average atomic mass on the periodic table. That's what molar mass is. And so we look on the periodic table, and it's right around 56 grams on the periodic table. So we're going to round a little bit, and we're just going to say that 1, and we'll do this in a different color. So 1 mole of iron is 56 grams of iron. And so those are conversion factors that we're going to use. Now, anytime we set up a problem, we start with the number that gave us to us in the problem. So 50 grams of iron. And then we look over here to our conversion factors. What conversion factor said grams of iron? Well, there's only one of them. It's right here. It says 56 grams of iron. That goes on the bottom. The other half goes on the top. Then we keep going. If we have more conversion factors, we keep going. So we look. Mole is right here. Got to put mole right there. The only thing that says mole of iron is that guy right there. Put the other half on top. And then we go ahead and we see that our units are going to cancel. Grams of iron cancels with grams of iron, moles of iron cancels with moles of iron. We're left with moles of iron 3 oxide, and that's what we want. So we multiply the top, 50 times 1 times 2, all divided by 56 times 4, and that will give us an answer of 0.446, and that would be moles of Fe2O3. So let's look at another example. Looking at this example, it says that an unknown quantity of ammonium phosphate is reacted with excess barium nitrate to produce 500 grams of ammonium nitrate. How many moles of ammonium phosphate were in the original sample? So here's ammonium phosphate, and then we have our ammonium nitrate, which is right there. So the first thing that we're always going to write down is our mole ratio, which is a 2 to 6 ratio. So 2 moles of our ammonium phosphate and that equals 6 moles of ammonium nitrate. Okay, so we always write down our mole ratio to begin with. Now we look at the problem, and since it said grams of ammonium nitrate, guess what we need of ammonium nitrate? We gotta have our molar mass. So when we look at our molar mass of ammonium nitrate, we add it up, where we're gonna have ammonium nitrate has 2 nitrogens, 4 hydrogens, 3 oxygens. It's gonna have a molar mass of right around 80 grams. So what that means is that 1 mole, let's pick a different color here, 1 mole of NH4NO3 equals 80 grams of NH4NO3. And now that we have our conversion factors, we can go ahead and remember we always start with the number in the problem. So 500 grams of NH4NO3 and set it up. What's the only thing that says grams? Well, that part right there. We put that on the bottom. We put the other half. Oop, don't want to move that too much. So we put the other half. It just doesn't want to move. The other half on top. And then we keep going because we haven't used all our conversion factors. And now what we're looking at is we have moles of ammonium nitrate. The only thing that says that, 6 moles of ammonium nitrate goes on the bottom. 2 moles of our ammonium phosphate goes on top. And we go ahead and we have everything set up now. And we see that grams cancel with grams. Moles cancel with moles. Multiply the top, so 500 times 1 times 2, all divided by 80 times 6, and that will give us a mole amount of 2.08 moles, and that would be of our ammonium phosphate. So looking at dimensional analysis one more time, we've gone from mole to mole conversions. Well, we can go again starting in grams, going to moles using our gram formula mass. Then we go from moles of A to moles of B using our mole ratio, and then we can go from moles back to grams by using our gram formula mass. And so we can see it set up here. We started with grams, we went to moles by dividing by our molar mass here, and then we changed it to CO2, and then we changed it to grams. The trick to this is it's pretty much the same problem. You just have to remember, if you see grams in the problem, you got to write the molar mass. So let's look at an example here. Uranium hexafluoride reacts with pure sodium in a single replacement reaction. We can see that down here that says how many grams of pure uranium can be extracted from. We have 2 grams of uranium hexafluoride, and we want to know how many grams of pure uranium. So we see that we have grams of uranium, and we have 2 grams of uranium hexafluoride. So when we're looking at this in the equation, here's uranium hexafluoride, and here is our pure uranium, which is right there. And so when we're looking at this, remember the first thing we always write down is we write down our mole ratio. So let's go ahead and do that. So 1 mole of uranium hexafluoride equals 1 mole of pure uranium. The next thing we do, since it said grams by pure uranium, it says grams of pure uranium, what we have to go ahead and do there is we have to go ahead and write the molar mass of pure uranium. So we look that up in the periodic table, and 1 mole of pure uranium is going to equal 238 grams of pure uranium. Okay, and then since it said grams of uranium hexafluoride, we then need the molar mass of uranium hexafluoride. So we'll go ahead and write that one down. So 1 mole of uranium hexafluoride equals our 352 grams of uranium hexafluoride. And all we did there is just 1 uranium plus 6 fluorines, and that's its mass. Now remember, every stoichiometry problem always starts with the same thing. It starts with a number given in the problem. So 2.000 grams of uranium hexafluoride. We start there and set everything up, and we go ahead and look. What's the only thing that says grams of uranium hexafluoride? Well, it's that part of the conversion factor. So we put it down there, and we put 1 mole, the other half, on top. And then we're going to keep going until we basically run out of conversion factors. And we look at it, since moles of uranium hexafluoride's there, that's what we need down there. The only thing that says moles of uranium hexafluoride now is that guy right there. So we'll put that back. Took a little bit too much. So there we go. There we go. 1 mole. Put the other half on top. And then I look. That says moles of uranium. So what goes on the bottom? We need moles of uranium. The only thing that says that is right there. Put the other half on top. And we see that we have everything set up. Kind of pull the whole thing a little bit farther down so you can kind of see it, because the picture's a little bit in the way. So we have everything set up all nice and neat, and then all we do from here is we go ahead, multiply 2 times 1 times 1 times 238, all divided by our 352, and what we see is we'll get 1.352 grams of pure uranium.